So I would like to start this talk today with a rhetorical question that Jay Krebs from Confluent asked during Kafka Summit in London this year. And it goes, would you blindly cross the street with traffic information that is 5 minutes old? Purpose of this question is for you to start thinking about the fact that we live in the real-time world, making real-time decisions based on real-time data. So why is it when it comes to our information systems that we are satisfied with old stale data? So often do we hear terms like D-2 data, meaning that we will work with data that is 2 days old. So when working with data, it's like we are living inside the matrix, if you remember the movie, where different set of rules apply as opposed to the real world. So my mission here today will be to pull you out of the matrix and bring you back to the real-time world. But in the end, the decision whether you will take the blue pill or the red pill will be completely yours. While you're processing all that, let me say hello to everyone and thank you all for coming to this session. I'm Sasa Kljaic. I work as a senior software engineer at Raiffeisenbank here in Croatia, and today I will talk about streaming data pipelines. Mainly what they are, why would we want to use them, and how do we approach to building them. To be on the same page, let's first define what streaming data pipeline is. And it is basically a sequence of actions that move data from a source to a target in real time. And what do we mean by real time? We mean as soon as data change occurs in the source system, it will be propagated to the target. During this talk, you will often hear the term latency. And it is basically the delay between the time when this data change occurred in the source system and the time when this data change was propagated to the target. When we talk about latency in streaming data pipelines, we usually express it in seconds or milliseconds, but it will never be zero. You will always have latency. So it would be beneficial, before we dive deeper into the topic, it would be beneficial to see the traditional approach. And in the traditional approach, we would have some kind of tool, whether it is a specialized tool for the purpose or some kind of shell script or whatever, that would move data in 3 phases. In phase 1, it would extract data from one or more source databases. Then in phase 2, it would transform this data in some kind of staging area. And then finally in phase 3, this transformed data would be loaded into the target database. The main characteristic of this process is that it runs in strictly predefined intervals, usually at the end of the day, end of the week, etc. And it runs, it processes the data, and then it stops. Because this process runs on a finite set of data, we call this process batching ETL. So what we want to do is eliminate this waiting before the next interval comes and process data as soon as it changes in the source system. That way, this process will run continuously and operate on an infinite set of data, and we call this process streaming. So why would we want to do that? Here's another example of the real world. Would you make an investment based on trading data that is a week old? I would say that even if you were interested in some stock or crypto or whatever, you would not dare to buy it unless you see the current data. And even if the historical data was looking promising, I think you would want to know what's happening right now with this stock or crypto or whatever. Another example, would you go on a field trip with weather data that is a few days old? Well, of course you wouldn't, and you shouldn't, especially to go to the mountains or on the sea on the boat. I'm showing you these glimpses of the real world. I'm tempting you to choose the red pill. So typical use cases of streaming data pipelines. I would say first, data integration. Anywhere you have multiple systems and one system depends on the data that is stored in the other system and cannot function without this data. So you want to minimize the data that this depending system is unable to function. I can share you a real life story, something that happened to me last year, I think. I wanted to buy something online and I wanted to go to the, and I went to the one of the largest online retail stores in the world. And I found the item, I put it in the cart, and everything went fine. But just before I finalized the order, I wanted to change my shipment address of the order. And because I have never ordered anything to this address, I first added it to my address list and then changed the shipment order of the shipment address of the order. And everything went fine. I reviewed the order details and clicked order, but I got an error page saying we couldn't place your order. There is something wrong with your address. And below that, it stated, fix your address or try again in a few minutes. So I was wondering what's wrong with my address. It's a normal address. And if something was really wrong with the address, wouldn't there be an error in previous steps? So immediately after that, I tried to click order again, but the same error page was displayed. So a developer inside me started thinking what could be the reason for this. And the strange idea occurred to me that maybe they have several components like ordering microservice, shipment microservice, and they are moving data in batches between them. So out of curiosity, I waited for 10 minutes and tried to click order again. And this time the order was successfully placed. I cannot be sure that my assumption was correct, but this is a clear example of bad customer experience, something that should not happen nowadays, especially for a multi-billion-dollar company. Some other specialized use cases of streaming data pipelines. Financial industries and real-time trading, where the difference between acting on the data now and acting several minutes later could be huge in terms of profits or loss. Marketing and sales, where you track user, where you receive large number of events about user activity, and then based on these events and historical data, you want to promote some content that is relevant to this user. Fraud and threat detection, where you want to detect anomalies in real time, and you want to stop fraudulent transaction before it is completed. Recommendation systems, Internet of Things, where you receive large number of events from your sensors and devices, and you want to detect faults as they occur. And what all of these use cases have in common is their unique ability to react to change. Something that would be really, really hard to do with the traditional approach. Because in the traditional approach, you would have to load all the data from the source, then wait for some time, and then load all this data again and then do a comparison of two data sets to be able to identify the change. So how do we get started with building streaming data pipelines? And we will solve a data integration use case where you have to combine data from one or more source databases and make it available to the target system in real time. I will show you 4 different approaches and I will evaluate each one of them based on the following criteria. First, we want to have a low latency of a few seconds. Introduction of streaming data pipeline must by no means degrade the performance of our source database or our source system in general. Next, we want to focus on delivering business value, not dealing with low-level technical stuff. Fourth, we want 100% data consistency. In some use cases like marketing and sales, if you lose an event or two, it's not of a big deal because the outcome will probably be the same. But in this case, we want 100% data consistency. And last but not least, we want the target system to be able to react to change. So when given some problem, we as developers often tend to think of the quickest way to solve the problem. So approach number one would be what I like to call poor mainstreaming. And it's basically an idea that we would use the existing ETL processes and just increase the scheduling frequency. But this approach only looks good on paper. In reality, if you have any non-trivial number of events, data changes occurring in your source database, you will never be able to achieve low latency. And because you're constantly polling the database, forcing it to read data from the disk, you will inevitably degrade the performance of your source database and your source system in general. Additional problem with this approach is that the target system cannot react to change because you are writing data directly into its database and it's unaware of the changes that are occurring in its database. So let's move away from ETL tools and try a different way. So we will try to inject event emitting code into the source application. So anytime that the data is written to the database, we will emit events to the outside, to some data interface. It doesn't matter what, like point-to-point interface like REST or MQ or Kafka. The first problem with this approach is that the code of our existing source applications, no matter how hard we try, usually looks something like this. And it's going to be really hard to pinpoint all the location where data is written to the database. And even if you say my code is structured perfectly, I know all these exact locations where I will put this code, you will have to deal with a lot of low-level technical stuff. For example, because you are doing two operations at the same time, writing to the database and sending events to the outside. What if one operation fails? Do you enclose these two operations in a global transaction, and then when one operation fails, then you roll back the whole transaction? But then you're introducing dependency and you're slowing down your existing transaction. What do you say if I ignore if one operation fails, but then you're introducing data inconsistency? So another problem with this approach is that if you have any reasonable number of events that you need to send to outside, you will inevitably have to introduce some kind of performance optimizations, because sending events one by one just won't cut it. So you'll have to introduce some kind of batching, take care of connection pooling, threading, and so on and so on. And the list of this technical stuff that you need to handle is really, really long. Trust me on this. Do not underestimate this list. So can we somehow ensure that when data is written to the database, that our code will be for sure fired? And we can create database triggers, and the database will guarantee when there is any insert, update, or delete executed on the table we are interested in, that the event emitting code inside the trigger will fire. So we took care of the pinpointing problem, but the list of technical stuff that we need to handle is the same as in previous approach, if not even bigger. So can we do something better? And in fact we can introduce the capture data change tool, or CDC tool in short. And it is a standalone piece of software that monitors database transaction logs and sends data change events as they occur. And because this tool does not query the database all the time, forcing it to read data from the disk, but it monitors database transaction logs, the performance impact on the source database will be minimal, because this is a highly optimized, dedicated tool for the task. It can achieve low latency that we need. And we don't have to write any code. We just tell it in what tables, in what databases are we interested in, and where to send data change events. And the data consistency is guaranteed by this CDC tool. If one of your components goes down, like whether it is the application, whether it is the database, Kafka, or the CDC tool itself, it will know when the problematic component recovers, it will know where to pick up where it left off. So no data is missed or duplicated or in the wrong order. So if it's not clear by now, we will use this approach and use Kafka as event streaming platform because it's highly performant, distributed, durable event streaming platform. There are others, but Kafka has been battle proven, so we don't have to think twice about this. So now we have data change events propagated to Kafka topics. And data change events from each table in the database are propagated to separate Kafka topic. But the database model is often, usually it is completely different than the source model. So how do we combine this data from separated Kafka topics so that it can be materialized by the target system? And there are multiple approaches to this problem, and we could evaluate each one of those approaches like we did earlier, but I will cut it short and say that the solution is to use some stream processing framework. And that stream processing framework in our case will be Kafka Streams. And Kafka Streams is a client-side library for streams processing where input data and output data are stored in Kafka clusters. What differentiates Kafka Streams from other stream processing solutions is that it is a client-side library, meaning that we do not need any dedicated stream processing server. It has a high-level DSL with declarative functional programming style. Declarative meaning we tell it what we want to be done, not how to do it. And this streaming DSL has all the basic stateless and stateful operators that you will need, such as joining, windowing, or aggregations. Because it is a client-side library for Java, it's very easy to get started with it. You just put a Maven or Gradle dependency in your project, and that's it. You're ready to go. And there are no external dependencies other than Kafka. Because Kafka Streams app is a normal Java or Scala app, you can deploy it anywhere. And you can leverage your existing CI/CD pipelines. And it's very easy to scale, especially if you have some kind of container orchestration platform where you just increase the number of instances and that's it. Stream processing logic is represented as a streaming topology, and that's a directed acyclic graph of stream processing nodes. And here you can see a very basic topology where we have data coming from 3 input topics, and we combine this data and publish it to the output. On the right, you can see the whole Kafka Streams code that you need to write to build this streaming topology. I have kept this example pretty simple because of a limited time and in order to be understandable to the broader audience. But I don't want you to think that I'm selling you some kind of theoretical knowledge of a technology that's used nowhere. So this is a real streaming data pipeline that we have built in the bank, built with the approach I have showed you and with the technologies I have showed you. And it combines data from 20 input topics about bank account data and provides it to any interested application in real time. If you remember, there was one character in the Matrix movie who actually took the red pill and went back to the real world. But after seeing what the real world really looks like, he regretted his decision and wanted to go back to the simulated world. And he blamed Morpheus for not fully informing him on how the real world really looks like. So that this situation does not happen here, I want you to be fully informed on how the streaming world really looks like. And coming from the batching world, and let's face it, we all come from the batching world, the streaming will at first look like a nightmare because we do not have the same luxuries as we are used to in the batching world. In batching, we run the job, let it process the data, and then we look at the final report to see if everything went okay. If it didn't went okay, we look at what was the problem, we fix some SQL comments, some logic or whatever, and then we run it again. We do not have the same luxuries in streaming. So you need to take care of some things before you rush into production with streaming. The first thing you need is a complete mind shift from thinking about data as data at rest to data in motion. And the closest analogy would be when you learn the basics of physics in elementary school, and then later in high school or in college, you went and tried to apply what you have learned on some problem on atomic level. And then they have told you that everything you have learned does not apply on this level. It's like that here. What you know about data at rest usually does not apply to data in motion. So what you need to realize is that in streaming, everything is done in parallel. And you have practically no guarantee in which order will the events be processed. So you need to really think about this parallel processing and what will be the outcome of your pipeline. What if one event is processed before the other? What if it's the opposite? What if one event is really late? What happens? So when thinking about, you really need to visualize this to yourself, what will happen out of your pipeline. And if you catch yourself waving hands like this guy, then you know you're on the right track with the mind shift. Because this process is constantly running, you need to allocate resources to it. By resources, I mean CPU, RAM, storage. Not enough resources and your pipeline will break, or it will not be able to process all the events it has on the input, and the lag will appear. Too many resources and you are paying more than you should. You are wasting resources. Also, you need to think about scaling and how many instances of your app do you need to process all the events. You need to think about the number of events you are receiving per second, and that this number will not be constant, but it will vary over time. You need to think about latency versus throughput, because it will be very hard to achieve both of them, to achieve low latency and high throughput. So you will probably have to sacrifice one of them. Because this process is constantly running, this process needs to be resilient. It needs to be able to handle errors and recover from them gracefully. And because there are so many moving parts in streaming, some people tend to use Lambda architecture. And if you're not familiar with it, it's basically saying that we will use streaming data pipelines, but we do not trust it to provide 100% accurate data. So we will use streaming for some gaining insights into real-time data, but we will not use it for anything serious. Instead, we will have the traditional ETL approach that would write data at the end of the day or whatever, and it will write its own data, and we trust in this data. Streaming leaders have been saying for years now that this approach, this Lambda architecture, is not really needed, and that streaming technologies are mature enough to produce the data in which we can trust. But I will not be an advocate for or against it. I can only say that we in Raiffeisen have streaming data pipelines that have been running for more than a year now, and they produce 100% accurate data. But again, it's for you to decide. And finally, streaming data pipelines need to be observed. You need to monitor them constantly. Unfortunately, Kafka and Kafka streams have tons of metrics that you can observe. If something bad happens, you need to trace what has gone wrong. And again, because Kafka Streams is a normal Java app, you can add your Java code and add additional logging or calling some external service or whatever. As you have seen today, benefits of streaming are numerous, allowing us to deliver real-time features that we have not been able to do in the past. So seeing this, do we replace all our existing data interfaces with streaming? I would say no. If you have, for example, a text report that you generate once a month, you send it to the government and you're done with it, there's really no point in doing this in real time. I would say in general, we do it where we have some business value, like improved customer experience, faster decision making, etc. So as you have seen today also, the streaming world does not look as beautiful as batching world. But advances are made as we speak to make streaming as easy as batching. But in the end, the decision whether you will take the blue pill or the red pill is completely yours. Thank you very much for attending this talk, and you're all invited to Raiffeisen booth where you can find streaming of free beer. So be sure to check it out. Thank you.